Hi there. As you arrive to this page, you already know what is FLUBIO, but let me give you a brief introduction. FLUBIO is an instructor parallel finite volume based in Navier-Stokes and convection diffusion like equation solver. So the solvers focus to research, but also is general enough to run industrial simulations. So it is based in Fortran and Fortran 2003 standard. So for those that know how to program Fortran will find this really easy, really handy. Okay, it's object oriented and organized in such a way that is easy to modify. Something important that is also, it comes with different models, okay, different solvers. So depending on what you want to address, you will choose a solver. So for the moment, we have these basic solvers: Poisson equation, Laplace equation, Burgers equation, general transform equation, and incompressible single-phase Navier-Stokes equation, laminar and turbulent. Okay, but it can be extended, and with time we're going to add more solver. What is important about FLUBIO is that we are using to solve the linear system arising for the discretization. We're using PETSC library, which is a library now for solving for the efficient solution, no, and scalable solution of linear system arising now for finite volume computation, finite elements, or finite difference. So theoretically speaking, it can reach exascale computing, and this is what we're pushing. Okay, we're doing our benchmarking, but all the actions of PETSC are exposed to FLUBIO, so you can use all those actions. Okay, and we encourage you to try to use all the actions and try to break the solver or break the PETSC library. Regarding the data structure or the elements that we can use, you can run cases in 1, 2, or 3 dimensions. Okay, it uses instructor meshes. Okay, and in theory it can handle any kind of element type. So tetra, hexes, prism, parameters, and general polyhedron. Okay, you can also handle hybrid meshes. So it's important that it does not handle hanging nodes. Okay, so if you have meshes with hanging node, that one cannot be handled. Okay, with FLUBIO. But you have the source code is the one you can implement that support, but we don't like to deal with that. When it comes to solver, the Navier-Stokes equation or the pressure velocity coupling, we use the standard methods. Okay, the simple method and piso method. Okay, the segregated standard method. It is in our plans to implement couple solvers. Okay, and also fractional step method. So to deal with the checkerboard instability, the classical rickshaw interpolation, many high order and high resolution methods are implemented for interpolation of the convective state, okay, which will guarantee at least second order accuracy. Also, when it comes to the time derivative, there are many methods implemented, okay, first and second order. Also, we have a steady methods. Also, we have the option for the diffusive terms. Okay, there are different methods implemented, and that is something also that we're working, okay, a lot, okay, to expose many options and let it to the user to know what is happening, and also many gradients discretization methods. Okay, and everything is implemented in a way that you can do it in a term by term basis. Okay, so you can have different methods with different orders of accuracy for every term that appears in your governing equations. Also to enforce monotonicity principle, slope limiters are implemented, the classical min-mod, okay, the classical theory, and for tourist modeling, runs and less models are implemented. So we follow here the standard finite volume method, okay, the finite volume method that you find in any of the classical books. Okay, we're following here, and we're just translating everything to something that is easy to read in Fortran for research, and we invite you to collaborate with us in trying to extend this work. When it comes to post-processing, everything is done using BTK, okay? So in particular, we're using a Fortran implementation of BTK. Here you have the link, and all the post-processing is done using Parallel, okay? So we're going to get the binary files, the BTK binary files, and then using Parallel, you can do your standard post-processing. Important that you get in the post-processing, you get the cell-centered values. Okay, so the method is collocated, we have the cell-centered data, but you can interpolate it using Parallel with no problem. And if you want more information, this is the initial article that we have, publication, so you have it here. Okay, you can come here, I have it, is the publication is open. Okay, and here you have a general description of PETSC, but we're working in some other more general applications, others in theory and application. So here, just to show you, for instance, on a steady case that you have it in the tutorials that comes here, we show now how to deal with unsteadiness, but also how to implement a non-uniform boundary conditions. Also, you have access to the traditional boundary conditions, Dirichlet, Newman, and Cauchy, the combined ones, but also you can have non-uniform profiles. Okay, so here we have unsteadiness, all the post-processing done using PotaView, and also here we have a very nice case, the Onera N6 Win. We didn't run in compressor, we don't have support for compressor. We're running compressor, but as you see here, we have very nice results and a comparison with other solvers, in particular with ANSYS, Fluent, and OpenFOAM, we have a very good agreement. So all these cases are distributed, and here you have all the general references. So at this point, just feel free to use FLUBIO, and please, we encourage you just to try to break it and let us know when FLUBIO is failing. So thank you for your attention. See you in the next video. Bye.